Welcome to Notes Video 1-11. It's a continuation of what we did in class. We're going to continue to approximate tangent slopes to the cubic graph that we looked at earlier. Okay, and today we're going to approximate the slope of the tangent line at the A value or X value or C value 2. So let's look at the notation required to show we're going to be finding the slope of the tangent line at 2. So like what we did in class, we're finding the slope of the graph at 2. We had the notation in class f prime of 1, and now we're looking at f prime of 2. And that little bitty notation right there calls up the limit of a difference quotient. So the y value at a point just nearby, real close to x equals 2 minus the y value at 2 all over delta x. All right, and before we begin to do any work at all, you might want to look at the cubic graph that we were working with the other day and just notice where a equals 2. If you find that point on the graph, a equals 2, you can clearly see on that graph that the function is increasing. So we know then that the answer to this question, the slope of the graph at 2, should be a positive number. If the graph is increasing, the rate of change is going to be positive. So at least we have something to work with. We know kind of a target value for us. We know our answer should be positive. Okay, so this just represents the slope of the graph at 2, and this is the work that we're going to do through limits to help us get that value. Okay, so what do we need? Well, we need the y value at this x value, and we need the y value at this x value right here. So we're going to come over here and do some work. This is the function we're working with. So first of all, let's go ahead and evaluate the function at 2. If you were to replace in 2 here everywhere, I'm going to get -1. You can verify that by looking at the graph. Okay, so that's going to be taken care of here. So now let's find the y value at a nearby point. Everywhere I see x, I'm going to replace it with input 2 plus delta x. Okay, we have everything we need. Let's come over here, keeping in mind that we want to keep the notation, keeping the limit notation as well. Okay, and to replace in here the y value that it's equal to, I'm just going to dump this whole expression right into the numerator. We're not finished. This whole expression would be the y value if we knew what 2 plus delta x was. It's going to be this right here. So let's come over here and subtract f of 2. Well, f of 2 is -1 all over delta x. Okay, and what we're going to do at this point is we're going to go ahead and expand this. And when I expand this, I'm just going to give you 4 terms. And those 4 terms are going to be the expansion of this binomial cubed all cleaned up. And again, these four terms that I just wrote down just came from the expansion of that binomial cube. So now let's jump back into the problem and proceed across here. So picking up the rest of the problem, when I distribute minus 12 minus 6 delta x, and then here I'll take care of cleaning this up, and this can be plus 4. So let's kind of see where we're at. Okay, so I've got the 8 plus the 4, which make 12. And that'll nicely cancel with that minus 12. And I'm noticing the remaining terms all have a delta x factor. You could take the time and collect these two delta x terms right here and have 6 delta x. Okay. So doing that, kind of clean it up here and put plus 6 delta x. Okay. We're still looking for the slope of the graph at 2. And through our work with limits, we're going to get that value. In the numerator, I factor out a delta x from this term. That leaves me 6 delta x. Take out a delta x here. Leaves delta x squared. And factor out a delta x here. That leaves me plus 6. And that works out nicely to factor or cancel these two, because that's what's causing us to divide by 0, and we certainly want to take care of that problem. So f prime of 2 equals, okay, my next move is to replace delta x with 0. I could clean it up a little bit, but to save some time and some work here, let's go ahead and plug in 0 here and here to this term, leaving us with 6. So this whole expression right here, when I plug in 0 for delta x, simplifies down to 6. So what we just found was the slope of the tangent line at 2 to that cubic we were working with. Okay, so just kind of paying attention to the notation right here. This is indicating slope right here. I want you to kind of look at the structure of this difference quotient right here. Notice that the clues in here, if we just solve this, the clues in this problem tell us that this expression represents the slope of the graph at 2. This 2 indicates that that's the particular x value at which we want to find the slope of the tangent line. And in the previous problem we did in class, we had a 1 here and a 1 here, and the notation here was f prime of 1. Those clues reveal to us that, you know, we're finding the slope of the tangent line at that particular x value. Okay, you know, that's all good and everything, and we're glad to get the slope. However, oftentimes you're going to be asked to write the equation of the tangent line at the point a equals 2. So in this case, we need to complete that process. So it's good to write in point slope form. It's easy. And to use the point slope form of the equation of a line, we need the slope, which we found. This is also slope m. We're going to say that's 6. And I'm going to use the point 2, negative 1. Okay, so y plus 1 equals 6 times quantity x minus 2. And it's just fine to just move the 1 over and solve for y. Of course, you could leave it this way, and that's perfectly fine too. No need to distribute. That is, in fact, the equation of the tangent line to the curve at the point 2, negative 1. Okay, so that's how we can find equations of tangent lines. All right. Now, what we could do is, we've only done 2 examples of finding slopes to this particular graph. We found the slope at a equals 1. We found the slope at a equals 2. What if I wanted to find the slope of that curve at 10 different x values? Well, this becomes a very tedious thing to have to do 10 different times. So we want a more efficient way of finding the rate of change, the slope of that cubic we were working with at many places. So instead of going through all this work, we can kind of step back and do a more general approach. Okay, so that's where we're heading to next. Let's say that I wanted to find the slope of the graph at any x. Now notice what I did here. I pulled back and I went to a general x. Okay, well, let's see how that transfers over here into our formal definition of a derivative. Be thinking ahead as you're writing. Think now, what is that going to look like based on the 2 examples that I did? Well, we're going to need the difference of 2 y values, one at x plus delta x, okay, and the y value at some particular x that I don't know yet. So the only change here is that these were 1 in the first example. These x values were 2 in the second example. And now here we're pulling back to a more general expression. So just kind of studying that right there. This still indicates 2 nearby points on a particular function. Okay? And what's going to happen is we're going to get a formula or a rule, if you will, for this cubic equation we're working with. We're going to get another equation with the variable x in it that's going to allow me to find the slope of the graph at any x value. Okay? So we've got our formula. Let's come over here. We've got our function. We've seen x plus delta x from a previous problem. Okay, jumping back into the problem. Replacing this notation with its y value. Subtracting, I used to have a numeric value, but now all I have is an expression depending upon what the x value is that I'm going to be using. So I need to make sure and put that in parentheses because I want to distribute the negative throughout the problem. Okay, expanding this. These first 4 terms I'm writing down are the expansion of that binomial cube. Now I'm going to jump back into the problem right here and distribute. Notice I need to distribute the negative throughout the problem. Okay, the x cubes cancel. The 6x cancels, and then, oops, this needs to be a minus. So I'll make sure that that's subtraction and not addition, so that this 3 will then cancel with that 3. Okay, the remaining terms should all have a delta x factor. Let's cancel or factor that out. So factoring out delta x from this next term, I did right here. Factoring out from the next term that has delta x in it. Moving over here, minus 6, that looks to be about it. Canceling the delta x's because that's what's causing us to divide by 0. I'm going to get rid of that situation. And I am going to clean this up. Looking at all the terms that have delta x in them, I'm going to replace in 0. Okay, and when I do that, I can drop, notice that's going to go to 0, that term's going to go to 0. Okay, I can drop the limit statement. I've plugged in 0 here. Now I have 3x squared minus 6. So what we just found was an expression, another function that represents the slope of that cubic graph that we were working with at any point x. So at this point, I'm going to go ahead and stop, and in the next video, I'm going to take a few more minutes and just kind of expand on this right here and what we're going to do with this. So this is a good place to stop, and I'll join you in just a second.